presentation on a novel FFT-based homogenization scheme for cohesive zones. This work was done in a collaboration with Ramin Moshfegh from Herr and Biel from Karlstadt University. So here you can see the outline of my talk. So first of all, I start with a short introduction into the topic, followed by an introduction into FFT-based homogenization. Then I explain how to adapt the FFT-based homogenization for cohesive zone modeling. And finally, I give some applications here, and I close my presentation with a summary and outlook. So first of all, homogenization, multi-scale modeling, is very interesting for the development of new and advanced composite materials. So you can design like a material. The idea is to design a material virtually in the future. So what you need is you have information on the microstructure, you have information on the mechanical behavior of the constituent, and you want to obtain a macroscopic response or at least an estimation of the macroscopic properties. And in this case, for the numerical part, here the FFT-based homogenization is expected to be faster and require less memory than the standard FEM methods. So, furthermore, the fracture behaviors of cohesive zone models, so the fracture behavior of full material layers like adhesive layers or thin sandwich material cores can be described by a cohesive zone. So here it's important to mention that the full layer is described as a cohesive zone. So if you model that, the element thickness is just the thickness of the cohesive zone, just one used for the whole layer through the thickness. Now the idea of this talk is to develop an FFT-based homogenization scheme to allow for the prediction of cohesive zone models from microstructure and the composition of material. So here on the right-hand side, you can see a scheme of scale separation. So we have a macro scale, which is homogeneous or treated homogeneously. And we have at each point at the macro scale, we have a related RVE, so representative volume element, which is heterogeneous. And besides the standard system of equation that you have for the macro scale, at the micro scale we have a balance of momentum, we have a strain compatibility where we directly distinguish between an average part, that is like the volume average part E, and a part that follows from the fluctuation displacement U star. We have a constitutive law and periodic boundary conditions. So this system of equation can be reformulated to the so-called Lippmann-Schwinger equation by introducing an isotropic linear elastic reference material, and we add C0 multiplied by epsilon and subtract it to sigma, and solve for U star. And then we have this solution operator here and can plug in U star into the strain compatibility equation and arrive at the so-called Lippmann-Schwinger equation. Here this gamma 0 operator is the solution operator for the strain field, and it's called the Green operator. So another important point is that the macroscopic strain is just a volumetric average of the microscopic strain field, which is here E, and the same is we assume the same for the stress field. So now, how to solve this Lippmann-Schwinger equation? So here I follow the work of Marzi Schneider. First of all, this homogeneous reference material is written as 1 divided by S multiplied by the fourth order identity tensor, and we arrive at S times this gamma operator for gamma 0. So here comes the Fourier transform into play. Gamma is known in Fourier space. So we need to transform into Fourier space to explicitly apply this operator because we know it there. So the most basic solution scheme is the so-called basic scheme, which is the gradual descent method. So first, in the first step, the prescribed average strain, so the average strain is always prescribed, is applied as strain field, and then in the next steps, here we have the next iterate here, and epsilon head is the Fourier transform of epsilon, and the zero frequency is E, and at all the other frequencies is just this expression here, and can be transformed back. So this can be also reformulated to using this property here, or the gamma operator, and then we have the increment of the iterate, of each iterate in Fourier space, that is here 0 at the zero frequency, and this expression here for all the other frequencies, and then the strain field can be updated according to this equation, whereby S is a step size, and for the basic scheme it's a fixed step size, that is just 2 divided by the maximum eigenvalue plus the minimum eigenvalue of the tangent stiffness. So we use in our code the so-called Basel-Bauer method, where adaptive step size every iteration is used. So according to this equation here, the step size is updated every step, and this is also the only change that is done to the basic scheme, and with this one we can achieve usually better performance at very similar numerical cost. So in addition, we use the finite difference discretization, the staggered grid one, for the gamma operator, and it's also important to mention that we have voxelized representative volume elements because of the FFT. Then in addition to the mechanical model, we're using a gradient ductile damage model, a non-local one. So here we have the local effective plastic strain and the non-local effective plastic strain that is regularized by the equation here. And then you have like a non-linear evolution law, for example, that is dependent on the non-local effective plastic strain. For FFT solvers, it's slightly different because the classical model is only defined in the damaging phase, but because of the FFT, we need an equation that is valid in all phases. So this is based on the work of that is cited here. So for this purpose, heterogeneous length, so we have this length parameter here L squared, and this is becomes heterogeneous at the microscale because it's basically close to 0 or 0 for a non-damaging phase, and the equation is also slightly changed. But if you assume a constant L squared, it's just the same again. This can be solved in a very similar manner, like the mechanical problem, by introducing reference lengths L0 squared. And here we use a fixed point iteration scheme. So we have here the inverse Fourier transform for the next iterate of this term here, and we have the Fourier transform of the local effective elastic strain of the non-local elastic strain of the previous increment. I is the imaginary unit, and xi is the frequency vector in this case. So, and then the coupled, so it's a coupled problem. We have a damage problem, and we have a mechanical problem. And the coupled problem at each time step here is used, is solved using a staggered approach. So we solve a mechanical problem, keep the non-local effective strain field constant, and then solve the damage problem. So for cohesive storm models, this picture changes slightly because we do not have a whole body that we want to homogenize. We have just a certain, like a cohesive zone, just this layer here, and the basic change at the microscale is that the thickness of this RVE is now the full thickness of the layer. So we need to model the full layer thickness for this. Then for the system of equations, there are only some very slight changes. So we assume that U star is 0 here at this boundaries. There's a prescribed delta. So for objective separation law, you have this separation vector delta here that you want to prescribe, and obtain then the stretch response or the traction response. And so you have mode 1, mode 2, and mode 3 parts, and U2 minus U1 is just the difference between the displacements here at the boundary layers. And elsewhere it remains periodic. So our solution to approximate this U star was just to add this stiff voxel layers here, that hinder the fluctuation displacement. And also, if you use this separation here, you can compute an average strain, or you can estimate an average strain according to this equation here. It's a Fock notation, and then the microscopic equation becomes just this equation here, just the volumetric average multiplied by the orientation. In this case, the orientation is just the 3 ring. So now let's come to some applications. And here we have hybrids, which is produced by Lamera. It's a sandwich material with 0.5 mm thick face sheets and a polymer fiber matrix core. Fiber matrix material model has been obtained from indentation experiments for yield plasticity and elasticity. I have a semi-periodical RE from this direction here, and this direction is not periodic because this is a layer boundary, and this has been generated with microscopy and CT data. And we also show some simulation results here for the U star. So it's a mode 1 experiment in Z direction, this direction. And we can see that the U star component in 3 directions is also pretty close to 0. So the approximation here seems to work quite well in this case. So then we have compared, we've performed some simulation and compared to experiments. So we've done we have performed a DCV test at Karlstad University. So some plates here were bonded to adherents, and you can evaluate the traction separation curve by the J-integral approach here. You can compute the J-integral from external boundaries. And then we have arrived at this traction separation curve. And then we have also done some simulations here, but the main idea was here to fit the damage model to this curve. But unfortunately, this is quite complicated at the moment because the computational times are pretty high on standard workstations. So we're extending that to a computer cluster. We're extending our code to a computer cluster. So for vegan adhesive layers, I refer to the next talk that will be given by my colleague Pauline Herr. She will give you some insights on how we are applying the method to adhesive layers. So, to summarize my talk, a novel FFT-based homogenization scheme for cohesive zone has been presented. This could allow for virtual material design of adhesive layer and sandwich material forms, but currently the computational times are rather high, and we need to improve this one, the current implementation, by trying maybe different algorithms or going to a computer cluster. And also further experiments are needed to evaluate the applicability of the method to practical materials. So thank you for your attention, and I'm looking forward to answering your questions.
Thank you, Felix, for your nice presentation. Questions, please?
I have a couple of questions. The first is, how much of the speed up do you get from FFT? How much speed up do you get from FFT?
This is highly problem and algorithm dependent, so it's in literature it's usually expected to be faster, but I haven't done my simulations in FEM and I haven't compared this, so I don't know how it is for my specific problem.
So you don't know if you get any basically. I think all the trouble going into the spatial time domain into FFT, but you should know how much benefits you get out of it.
Yeah, usually it's expected to be faster, but it somehow depends. It can be. It depends on basically on the material contrast that you're having. So.
Anyway, my second question is more.
I'm not really sure how it is for this problem, but.
We did also work with these DCP geometries and so on, and yes. I've looked into your prediction, but we have also oscillations in the low displacement curve, which is not usually what you get. But the prediction with the simple linear triangular CZM works very, very fine with these DCP geometries. I'd say better than what you presented with your FFT-RE homogenized.
Yeah, so the idea is not to do experiments, but to have like to get the traction separation response in advance before or without doing experiments, and just using experiments as validation, so that you can optimize your microstructure or optimize the materials that you that you put in into your material. It's for material development. So it's not for like to replace a certain Kamani-Davila model. So this is not the idea of this homogenization principle.
Okay, thank you. Thank you very much.